Minerals are really, really important to us in many different ways. In geology, minerals are important because they are rock-forming materials. They make up all the materials of the earth, but also they make up the things that we use in everyday life. Everything from the very, very small minerals that make up computers and cell phones, but also things like gypsum that goes into wallboard, or calcite that goes into making heartburn medicine, to graphite that goes into pencil lead and things of that nature. So minerals are very important in many ways. Alright, so what I have up here on the screen is a question. What's the relationship between all of these? And I'm going for, let's go from the bottom down here all the way to the top. So at the bottom you have basically I have a question mark, but what you have is the crust of the earth. So the crust, the soil, rocks, all that stuff, it makes up the crust. Within that you have rocks, the solid rock materials, which we'll focus on next class. And then what makes up rocks are minerals. What makes up minerals are elements. Within those elements are protons, neutrons, and electrons. And inside of protons and neutrons you have these really small particles called quarks. Now this class is not a physics class, so I'm not going to get into the details of what quarks actually are and how those things work, but I do have a few slides if you're interested in knowing more about those coming up. So this is just a review. Most of you at some point in your life have had a chemistry class or a physics class, whether it's high school or in college, or perhaps even an earth science class. So if you're interested or you just need a review, this stuff is kind of important to know. For example, how is a molecule related to a compound? What's an atom? What's an element? Is there a difference? So I've just basically put this slide up here for your information. So quarks were proposed in the 1960s, and these are these really small particles. Like I said, they're comprise protons and neutrons, and they have ups and downs. And I don't really need you to know that much about quarks, other than they are what determine the charges of protons and neutrons. Protons are positive, as you probably know, and neutrons are neutral. So those determine the charges of protons and neutrons. Electrons are really, really small, and they float around. They circle around on the outside of the nucleus of an atom, and those are about 1/2000th of the size of protons and neutrons, which are made up by quarks. And there are plenty of different quarks out there. We weren't able to identify what quarks were until later on, but now we've been able to show there actually is such thing. Back in the 1960s, we just had proposed that there was such thing. But anyway, again, this is not a physics class, so I won't go into that in any more detail. Then you have elements. I'm sure many of you are familiar with the periodic table of the elements. We're going to talk about how to read this in a little bit. On the left you have a pie chart that shows you the relative abundance of elements in the Earth's crust. What you'll notice, and this is very important, this may be a test question, is that oxygen and silicon are the two most common elements in the Earth's crust. That's important because those are very common elements that make up important minerals, abundant minerals. So you can click there and you can find out more about any element you want. The dynamic periodic table is a really neat thing. So I have a question here. In my in-person classes, what we do is we stop here and we take a look at all these different things, and we try to determine which ones are not minerals and why. We're moving on beyond elements now. So the first one here is the ruby that goes into making a laser. So you have a ruby, goes on the inside, it collimates those lights and it produces, well, laser focused beam. And the second one is petroleum, is oil. Third one is sugar. The fourth one is coal. The next one is salt, and the last one is ice. In the case of a laser, rubies are actually made in the laboratory. So in this case, rubies that are made in the laboratory are actually considered not minerals because they're made in the laboratory. Minerals have to be naturally occurring. They're made in the laboratory to get out any impurities, and it helps collimate the light better. So that one's not considered a mineral. Second one, petroleum, is not considered a mineral because it's liquid. It has to be a solid to be considered a mineral. The third one is sugar. And sugar is a plant product, so anything organic is not it has to be inorganic to be considered a mineral. Sugar is organic, obviously, so it's not considered. The next one down here is coal. Coal is actually a rock, and coal is made out of ancient plant life that was around 300 or 400 million years ago. So even though it's Kentucky state mineral, it's really a rock. Salt is a mineral. It is sodium chloride, the chemical formula is sodium chloride. And the last one is ice, and ice sometimes is confused. This one actually is a mineral. It has a chemical formula. It passes all the tests on this slide here. These are the 5 requirements of a substance to be considered a mineral. And this would be important to know. Naturally occurring, solid, inorganic. It has to have a chemical composition, and this is a part of the definition of a mineral. For example, calcium carbonate, that is calcite, which makes up the rock limestone. Sodium chloride makes up salt. So if you were to take that NaCl or that CaCO3 and adjust it some way, put something else in there, it would not be the same mineral. It would be a different mineral. That's why that's important. And the last one is a reasonably definite chemical or crystal structure, excuse me. If you look at minerals on the small scale, they have a crystal structure. So here's the periodic table. I'm just going to move a little bit more quickly now. This is just to review the parts of an atom. Here you have the nucleus with the protons and neutrons, and you have the various electron clouds on the outside of it. I do want you to know what the atomic number is. The atomic number is the number of protons in the nucleus, and this is what defines the element. So on the next slide we're going to see the periodic table, and up here on the top left, sometimes it's on the top right, but up here on the top left on this periodic table you have a number 1 beside of hydrogen. That's the atomic number. Number 2 over here is helium, lithium, beryllium 3 and 4, so forth and so on. That's the atomic number. That's what defines the element. Here are just some examples. Iron on the left has an atomic number of 26. You got 26 protons there. And uranium over here, you have 92 protons in the nucleus. And also, whenever you have whatever number of protons you have that same number of electrons because they're neutral. The neutrons can vary, though. We'll talk more about that in a little bit. It's called an isotope. The atomic mass is the number of protons plus the number of neutrons. So in this case, carbon, and this is what determines the weight of an element. And in this case, it's carbon. You have an atomic number of 6. You have an atomic mass of 12 because you just add those two together. So that's the atomic mass. That's also important to know for when it comes exam time. It's important for us to know and understand a little bit about chemistry. We're not going to get into chemistry in any amount of great detail in this class, but it is important to know some of the basics. So the first part of this lecture will cover some basic mineral chemistry. So here on the periodic table is where you find the atomic mass number. So you can see hydrogen is 1.007 something. Helium is 4.002. In most cases it's about twice this number at the top, twice the atomic number. As I mentioned a minute ago, isotopes are elements with different number of neutrons than protons. Here's an example of that. Oxygen. This is the most common form of oxygen. You have oxygen, what's referred to as oxygen 16, which means you have 8 protons and 8 neutrons. The atomic number of 8, the atomic mass of 16. But occasionally you can get oxygen isotopes that have different numbers of neutrons. In this case you have 9, and the atomic mass would be 17. In this case you have 10 neutrons, and the atomic mass would be 18. Now these are really important. We'll talk more about this when we get to the climate change section, because these isotopes, these oxygen isotopes, help us be able to determine what ancient climates were like. Also, something important to know, an ion is a charged particle. You can have negatively charged or positively charged. The negatively charged ones are called anions, which are important to the silicate minerals at the end of this lecture, and cations bond with those to make minerals. That's the important thing in making minerals. Right now we're talking about elements. How do these elements come together to form minerals? It all has to do with ions. A note down here at the bottom, one of these always super dominates. In most cases it's the one like this one, 8 and 8 for example. Atomic number of 8, atomic mass of 16. This makes up, probably, I don't know the exact number, but this makes up probably 99% of the oxygen isotopes. Valence shells around the nucleus have a certain number of electrons they can hold. In the case of hydrogen, it's 2. In the case of carbon, the first shell is 2, the second shell is 8. And in the case of oxygen, for example, the first shell is 2, second shell is 8. And it gets more complicated after that. But it's important to know that the first shell can hold 2, then it's full, it can't hold any more. And then the second shell holds 8. And that's what's important for purposes of this class anyway. For this lecture anyway. Noble gases. Noble gases have the maximum amount of electrons in the outermost shell over here. So they don't like to bond with anything else. Alright, so all the other ones want to bond when their outermost shell is not full. And there are 5 different kinds of bonds you can have. The ones we're going to focus on most are ionic and covalent, so we'll see those on the next slide. But you also have van der Waals bonds, which are these really weak bonds. They're kind of equivalent to getting your clothes out of the dryer with static charge. It's like turning pages in a notebook, basically. You have a mineral they're basically grouped as micas, called biotite muscovite, and they're held together in that direction by these weak bonds. Then you have metallic bonds. These are bonds in which the electrons are free to move out throughout the entire mass. Let me move this down so you can see my hands moving here. So if you have something that's metallic, something that's metal-like, in the case of something that's metal, you have those electrons, they're moving throughout the entire mass. Those are good conductors of electricity and temperature, so those can conduct. The hydrogen bond is related to water bond. So let's talk a little bit about an ionic bond. Here's an ionic bond of halite, and remember it wants 8 in the outermost shell. We don't have that, so we're going to have to do something. Nature does it for us to create a bond that it wants. The two are attracted by the charges created. So the example we have here on the left is a sodium ion. The one we have on the right is a chlorine ion. Here, these numbers up here correspond with the number of electrons in that shell. So as I mentioned earlier, you have 2 in the first shell, 8 in the second shell, and you want to have 8 in the last shell. In the case of chlorine, you have 2 in the first shell, 8 in the second shell, it's full, and 7 in the outermost shell, it's not quite full. So the most convenient thing for these to do is for sodium to lose an electron, to give up an electron to chlorine. This gives out a weak mathematical charge, and you have a +1 here and a -1 here, and that holds them together very weakly. So ionic bonds are very weak. This is an example of what halite looks like. What you'll notice is that it has mineral cleavage. I know it's a funny word, but mineral cleavage. That means a straight face that tends to break off, and it looks like this. And the reason why it looks like that, even under a microscope, when you're eating table salt, halite, if you look at it even under a microscope in the smallest of ways, it always has these cubic shape to it, cubic cleavage. And the reason it has that is because of these sodium ions and chlorine ions come together. The next one is a covalent bond, and covalent bonds are very, very strong. These are the strongest type of bonds. So over here on the left, you have, these are carbon, and the first one, again, it's full, so you have 2, and the second one, it's not full, it has 4. So you have one over here, another carbon bond that's 2 and 4. So the most efficient thing for it to do is to get together, share that space, and for those on the outside, for those 4 on the outside, to travel throughout the entire mass. And when it does that, it's a really, really strong bond. And I have a picture of a diamond down here because this is how diamonds are formed. And as you know, diamonds are very strong. You can't really break up a diamond. It's very difficult to do so. So, and diamonds are very hard. They scratch glass. They're the hardest mineral. So here's an example of two minerals that have completely different properties, but they have the same chemistry. So they're both made out of carbon, but one is covalently bonded all the way, like diamonds, and down here you have an example of graphite, and it's not covalently bonded. It has van der Waals bonds, these weak bonds in between it, and that's why a pencil writes, basically. It's made out of this, and you're breaking those van der Waals bonds. Chemistry is important, as I alluded to earlier, because it determines the properties of mineral. And again, this will be on the exam, so it's important to know that. So we're going to move on to the second lecture. I got through that really quickly. So if you have any, if you didn't get all that, feel free to go back and watch it again. So we talked about 8 elements in the crust of the Earth. I showed you this chart at the beginning. These 8 elements make up virtually all of the Earth's crust. Now there's another, that's 98%. There's another 2% that makes up everything else. But oxygen and silicon are very important, and you've all heard of these things: aluminum, calcium, sodium, iron, so forth, magnesium. These are all very common elements that make up minerals. So I want you to pay specific attention to silicon and oxygen. Silicon and oxygen are elements that are very important to making up the 2 biggest mineral groups. I want you to know the difference between groups and species. So there are 2 main mineral groups. 2 main mineral groups. Within those, there are lots of different. Within those, there are subgroups, and within those, there are thousands of actual mineral names, and we refer to those as species. Now, hopefully this is not confusing to you. If it is, you'll see what I'm talking about on the coming slides, because I've already put it in a chart together for you. All right, now we're moving on to minerals. We're moving on to actual minerals. In the last pie chart, we talked about elements and how those elements came together to make minerals. Now we're going to be talking about the abundance of minerals in the Earth's crust. So again, there are 2 main groups. Those groups are the silicate minerals and the non-silicate minerals. Silicate minerals make up just over 90% of all minerals in the Earth's crust. And we'll discuss these silicate minerals first. Toward the end of this lecture, we'll talk about the non-silicate minerals, but in the first part here, I want to focus on silicate minerals. So of the minerals, this is also important to know, an important chart to keep in mind. Of the common minerals in the Earth's crust, 51%, if you add up 39 and 12, about 51% of minerals, about half of all minerals, are feldspars of one type or another. And the second most common mineral is quartz, and there are a bunch of other things in there as well. And we'll go through this in a bit. So, talking about silicate minerals, all silicate minerals have something in common, and that's because they have this arrangement of atoms. It's called the silicate anion. Remember, we talked about ions earlier, being charged particles, and an anion is a negatively charged particle. So in this case, you have silicon, which has a positive 4, and you have 4 oxygens around it. Each of these has has a negative 2 charge. So if you add all this up, that's a plus 4, minus 2, minus 2, minus 2, minus 2. That has a charge of negative 4. So this negative 4 charge, this anion, wants to pull in positively charged things to neutralize it. So what does it pull in? It pulls in cations. So here are the common cations. Calcium, as we said, as you saw earlier in that pie chart when we were talking about elements, calcium, magnesium, sodium, potassium, aluminum, and iron. And those are the relative sizes and the relative charges over here. So these cations are used to balance charges associated with anions. And this is important because this is how we get the vast majority of our elements from minerals. In nature, whether they're floating around in water or soil, or they're becoming evaporated, they're coming out of a volcano, this is how these elements come together to form all the minerals of the Earth. There's so many silicate minerals that we have to subclassify them. And we do this based on, and again, I have this in a chart for you later, so if you're confused, you can always go to that chart and it will have the answers for you. But we're subdividing the silicate minerals into two subgroups here. You have ferromagnesium. It's just a fancy word that means that it has 2 basic ingredients, can be iron or magnesium. And because of that, if you look at the atomic mass, it's heavier. You know, they're denser, heavier, darker in color. And on the right side of this chart, we have non-ferromagnesium, which simply means it does not contain iron or magnesium. In its place, it usually contains aluminum, except for quartz. You'll see that in a minute. Here are 4 common ferromagnesian silicate minerals. You don't have to memorize the chemical formulas or anything, but I do have them up here conveniently for you, color-coded to show you what these things mean. First of all, just the minerals. Don't pay attention to the groups right now. Olivine, augite, hornblende, and biotite. Those are the 4 common iron and iron and or magnesium silicate minerals, or ferromagnesium silicate minerals. So the iron and magnesium are in red, and the silicate anion is in green. Everything else in white are just extra elements that are put in there to give it some extra flavor or extra coloring or that sort of thing. So those are the ones on the left side. We're going to move on to the ones on the right side, which are the non-ferromagnesium silicate minerals. They usually have aluminum in them. Now this is just a complex chart that if we were talking in detail, if this was an upper level class, we would spend more time on what this actually means. But in this class, I just want you to know these are the feldspars. So feldspars are complicated. As I mentioned, about 51% of all minerals are feldspars, but you do have these subgroups of feldspars. You have the plagioclase group and the potassium. That K means potassium, feldspar. So they're basically just three different types of feldspars. I'm not going to get into that in great detail, but I do want you to know that this is plagioclase feldspar over here, and this is potassium feldspar at the bottom. Plagioclase feldspar is lighter in color, and down here at the bottom, as it indicates, it's lighter in color and commonly has striations. These are parallel growth marks on the minerals. Down here, the potassium feldspar is more like a pinkish color and does not have striations. And the other two on this side, the non-ferromagnesium minerals, are muscovite, which is a really cool mineral. I was talked about it earlier, the mica mineral, muscovite. It's kind of like a book. You can just peel the pages off of it because it's bonded by those very weak van der Waals bonds. And on the right side over here, you have quartz, which is a very unique mineral. You've all heard of quartz. You've heard of quartz watches. The quartz is used in all kinds of things. And here's what it looks like when it grows freely in crystal form. We'll talk more about quartz when we get to the end. All right, so here's the first part of the chart. These are all the common silicate minerals, and notice there aren't that many of them. We only have 7 on here, so that makes it easy enough, right? So these will be good to know. So on the left here you have the ferromags, olivine, ologite, hornblende, and biotite, and on the right here you have the non-ferromags, feldspars, muscovite, which both have aluminum, and then quartz, which is simply a silicate anion, and that's it. All right. So if I were to ask a question like this, you'd know the answer, right? It's important to know. Which are the most common? Which minerals are the most common? All right, now we're moving beyond that. We're moving now on to the other side of things. What about non-silicate minerals? This is going to be the second big group of minerals. And again, I will add these to the chart and show you at the end. Important non-silicate minerals. We'll get to the actual minerals themselves in a minute, but I want to tell you a little bit about non-silicate minerals before we move on to that. First of all, about 10% of minerals in the Earth's crust are non-silicate minerals. So they don't really make up a huge percentage of minerals, but they are important as well. There's no silicate anion in non-silicate minerals. So with the silicate minerals, they all had something in common. They all shared that silicate anion. In the case of non-silicate minerals, they don't have that. They don't have a central core structure or central core chemistry. There's just simply no silicate anion, and that's the only thing they have in common. A lot of times these minerals are economically important, not quite as abundant. Calcite's an exception to that. Calcite makes up the very common rock limestone, which we have all around Kentucky. It's the reason we have so many caves, and in Florida and some other places too. But Mammoth Cave's the biggest. So we'll discuss Mammoth Cave when we get to that section. We'll talk about limestone in the next. I believe it's the next few classes. But anyway, calcite is important because it makes up the rock limestone, which is a rock-forming mineral. These are some of the other minerals that we will briefly discuss in this section. Hematite, magnetite, limonite, calcite, dolomite, halite, gypsum, and pyrite. I have some minerals here on the slide. Hematite is the one I'm going to focus on first. Hematite, as you see, is Fe2O3. That's iron oxide. The Fe is iron, the Fe2 is iron, the O3 is oxide. This is what's referred to as an ore mineral. So it has iron in it. We want to get the iron out. What we do to get the iron out is we melt it and we can get free iron, and we can mold it into any shape we want, and we can make bridges and buildings and all kinds of things with iron when we do it that way. Also, we can add varying amounts of carbon and make steel with it, and here's some videos on how we did that, both in the early days and now, so feel free to watch those in your spare time. And also you have magnetite, which is also an iron oxide. It's magnetic. And here's another version of hematite. There are two different types of hematite here. One is kind of plain looking, and the other one is very metallic. So those are, most minerals aren't like that. You usually don't get two versions that look very different. Anyway, going back to hematite. A student one time asked, what's the most important mineral with respect to human evolution? And the answer to that question, I think, would probably be hematite, because hematite's what got us out of the Stone Age, as you see here, through the Bronze Age, into the Iron Age. Before we were using iron, we were using, simpler things to build things with. Probably what happened thousands of years ago, you had these cavemen type people, I guess you would say, who were sitting around this fire, this huge bonfire, and they had these rocks with hematite in it, and realized that it was leaking out liquid iron for a while, and they probably realized that it was malleable. When it's hot, you could pound it into things that later led to ironsmithing and that sort of thing, and you started making things out of it. So, now we've, obviously with better technology and such, we've streamlined that process, and we can make whatever we want out of it. So that's hematite, and that's called an ore mineral. When you have something inside of the mineral that you want to get out, you have to manipulate it somehow to get that mineral out of it. You don't just have free iron sitting around, because we have oxygen in the atmosphere. If we were to have free iron sitting out, it would combine with that oxygen. It just has a tendency to do that. I break the rules on PowerPoints in this class because you're not absolutely required to have a book, so I'm breaking the rules of PowerPoint and putting lots of words on the screen here. But we're talking about calcite here and dolomite. These are two very important non-silicate minerals. Just to give you some examples of the things that calcite are used for, first of all, it makes up the rock limestone and marble. It can be used for all kinds of things. It forms chemical precipitation in shell material, so there are lots of shells out in the ocean made of this stuff because there's lots of calcite floating around out there, calcium floating in the ocean. It's also a deposit in caves, as you may have heard, stalactites or stalagmites. Some other examples, it's used as dimension stone in the rock form. We make buildings with it. Blocks for the pyramids are made out of it. Modern construction uses it to produce cement, concrete. We use it as acid neutralizers. I use that after I eat a bad meal or something to neutralize stomach acid, because stomach acid can be very bad. It can have an acidity down to 2 or something like that. So you want to have some way to neutralize it by putting in calcium into your body in the form of calcium carbonate in powdered form in a Rolaids or a Tums or something. Look at the ingredients. It has calcium carbonate on it. And it can be used for other things as well. Paint, dietary supplements, so forth and so on. So calcite's a very useful mineral. Just a few other examples of minerals that are important. Halite. Halite is table salt. There are several different kinds of salt. This is a common one. It's used for our diet, obviously, that we eat and animals eat and so forth and so on, but it's also used in this part of the world, at least, with highway de-icing, because it gets cold in the wintertime and this changes the temperature at which ice can freeze, so it tends to melt it at least down to a certain temperature. I can't remember exactly what that is, at 12 or 15 degrees Fahrenheit maybe. It's used in other things as well. You can read through this. Gypsum is used in wallboard, plaster, agriculture, cement manufacture. If you have wallboard, sheetrock, some people call it, in your house, if you break it, you see the little dust coming out of it. That's gypsum. It's also produced as a byproduct of coal-fired power plants, if you've ever seen that. So some of it comes from there these days. You have pyrite down here at the bottom. It's an iron sulfide mineral. It's commonly associated with coal. So it's an impurity in coal, and it's referred to as fool's gold when we find it in Kentucky. We don't have any gold really in Kentucky, so we do have lots of pyrite though, so we call it fool's gold. Here's a summary of all the minerals that we've discussed. So I told you at the beginning we have the silicates, That's a group all on the left side, the first two columns here. These are silicate minerals with the subgroup iron and magnesium, the ferromagnesians. Here's the silicate minerals with aluminum. And over here on the right side, now I've added the non-silicate minerals. So here you go, all in one wonderful little chart that pulls it all together, everything we've talked about today. These are the common minerals. You know, there are over 4,000 minerals out there, but as far as the ones that are actually common, here are the common ones, all in one chart. All right, here's the economic geology slide. This is a little old, outdated in a book I used to use, but it's still useful. You can follow these numbers down to the bottom, and it'll tell you what types of things are in that product that we use. For example, a computer. It has gold, silica, nickel, aluminum, iron, zinc, petroleum, and 30 or so other minerals in it. A camera, you can tell this is old because the camera looks old, and it also has a BlackBerry. Do people still use BlackBerries? I don't know, but it has gold, nickel, petroleum products, silica, so forth. Wallboard back here, 14, it includes gypsum, clays. I'm sure there's a pencil up here. Yeah, pencil number 2 includes graphite, clays, so forth. Stereo, old school stereo. Now look at the TV over here. That's nice. Okay, so just to give you some examples. So everything around you, well, most things around you in one way or another are related to minerals. I'm not going to go through all these, but here are just some other uses for minerals that we haven't discussed yet. So, and here's a really neat video on quartz, on how quartz is used in the making of watches. So quartz has this really unique property to it that if you apply an electric charge to it, it vibrates at a very, very fast frequency. I believe it's 30-some thousand times a second. I haven't watched this video this semester. But it vibrates very, very quickly, so it can keep very accurate time. So if you want to watch the video, it only lasts 3 minutes. It's interesting. Okay, so we've gotten through that in a little over 30 minutes. I want to spend the rest of today talking about mineral identification. If you happen to watch this before your lab tomorrow, this will be helpful to you. If you watch it after your lab, it'll still be helpful to you, but maybe it'll make more sense to things that you talked about beforehand. So I wanted to make the point, first of all, there are over 4,000 minerals that have been identified and officially accepted by the International Mineralogical Association. That's the official group that says, yes, their responsibility is to take a look at something and decide whether or not that's a unique mineral. And yes, there's a group of people that do that and decides that sort of thing. So there have been over 4,000, but only about 24 or so are abundant. And to put that into perspective, two of the most common minerals that we discussed earlier, feldspar and quartz, make up 63% of all minerals. So the question that sometimes comes up is, what are the different methods of mineral identification? In other words, are there ways to definitely tell what a mineral is? People bring me rocks and minerals all the time, and they think they found something unique, and a lot of times they have found something unique because of the way it looks. But as far as the chemistry of it goes, it's oftentimes not unique. But there are ways definitely to test it and to find out if it truly is a unique mineral, for example. Now, this doesn't happen very often. Let me be clear, but there are ways to tell. So some of these ways include XRD, XRF. These are just huge machines that cost hundreds of thousands or millions of dollars that can scan the inside of them and test the chemistry or the crystal structure, scanning it down to an electron level to see what the crystal structure is of these minerals. It's kind of like having an MRI in a way of minerals, in a way. And then you have ICP mass spec down here. That's just another complicated way. So obviously we can't afford to do things like that. So what we do at our laboratory is we just use the traditional method. We could use optical mineralogy, look at it under a microscope, but those are kind of expensive too. So what we do is we use the traditional method of hardness, testing the streak, just its overall appearance, what's its color, these types of things. And using the charts that we use in lab, you can get pretty good at this in a matter of 2 classes. And most students get the majority of them right in the first class. So first of all, I want to talk to you about how to go about identifying minerals. So you're going to be given this chart, And you're going to have to follow the chart. One of the first things in it's going to say what's the luster of the mineral. Then it's going to ask what the cleavage of the mineral, what's the hardness, and you just follow along, and it will get you to the right answer if you make the correct observations. Which, when you work in a group, that's pretty easy to do, I think. So one of the first ones is luster, and what luster is how it behaves in light. The first example is metallic. I think most of you have an intuitive sense as to what metallic looks like. It's just metal-like. Light hits it, it reflects off of it. It's opaque, meaning light cannot pass through it. If you cut it into a thin section and looked at it under a microscope, light would not pass through it at all. You can't really tell that just by looking at something, whether light can pass through it, but you can tell if it looks metallic or not. So most students you find this pretty easy to do. The opposite of that is non-metallic. Now, non-metallic is basically everything else but the metallic minerals. Non-metallic minerals, this is an example of what a non-metallic mineral would look like. It can this is just one example, it can either look glassy, it can look transparent, you can see through it, it looks earthy, just like a normal rock you would pick up or a mineral you would pick up out of a stream, it looks muddy, it just, anything else but metallic. Don't confuse that. Anything that looks metallic is probably metallic. Anything that looks anything else is probably not. There aren't that many metallic ones. Most of them are non-metallic. Color is another one that is not as reliable. Now, in some cases it can be reliable, but the point on this slide I want to make is that color is not always a reliable factor in identifying minerals. Here, for example, you have 3 different varieties of quartz. The one on the left here is just a plain clear quartz. The one on top is a rose quartz, and the one on the right is a smoky quartz. Those are all the same. They all have the same properties and chemical properties and all that stuff, but they're slightly different because they have a different color. So if you were just looking at this based upon color, you might misidentify it. So note that color is not always reliable. So you won't be asked color, you'll just sometimes note it in the comments. One thing that you will be asked, though, is does it have a cleavage? The opposite of cleavage is a fracture. So as I mentioned earlier, cleavage is a tendency to break along these planes of weakness. And when that happens, you have a flat surface. In this case here in top, you have halite. This is what's referred to as a cubic cleavage. You can see the 90-degree angles on there. So that's one with cleavage, and the one down here is an example of a fracture. I like to think of a fracture as, well, basically the opposite of a cleavage. If you break something and it breaks in a random pattern, it does not have a flat edge, kind of like a bone fracture, then you have a fracture. So going back to cleavage, though, on this chart here on the right, you can have minerals that have different numbers of cleavages. For example, you can have a one direction of cleavage, just one flat mineral. For example, a flat piece of paper would have one direction of cleavage, one cleavage to it. You have 2 minerals that you'll see that look basically like a sheet of paper. One's black and one's white. Muscovite and biotite. And here's some with 2 directions, meaning you have a flat surface in that direction and a flat surface in that direction. That's 2 directions of cleavage. Feldspar is an example of that. Down here's 3. Halite's an example of that one. In a case of 3, you have 1, 2, 3, and that third one out there, and that third axis out there, and that would be a shape of a cube. So you'd have halite. And they don't always have to be at 90-degree angles. A lot of times they are not at 90-degree angles. And you can get up into the more complex ones like 4 directions, which create some really interesting shapes like fluorite. You have a porcelain streak plate that's white in your lab tray, and you can rub the minerals over them and it will leave a streak in some cases, and that streak may help you identify what the mineral is because it will tell you about it on your identification chart. Here's a really important one, hardness. You move myself out of the way so you can see the chart over here. Hardness is how a mineral reacts to other things that you scrape it against. For example, you might scratch it against glass. You might scratch it against your fingernail, which is very soft, by the way, has a hardness of 2.5. It tells you right here. Copper penny has a hardness of 3.5. A wire nail hardness of 4.5, and a glass plate. That's the most important thing, because you will have a glass plate, and this is what you base the hardness of minerals off of. If it has a hardness of greater than 5.5, it's considered hard. If it has a softness of less than that, of less than 5.5, it's considered soft. And the streak plate 6.5. So here's some common minerals. You'll see talc, you'll see gypsum, you'll see calcite, fluorite. But the only other one up here that you'll see in lab is quartz. So quartz has a hardness of 7. That means if you scratch it over a plate, it will scratch the plate because it has a hardness that's greater than the hardness of the plate. Diamond's way up here at the top. It's much harder than any of these other ones. Talc is so soft that you can scratch it with your fingernail. Your fingernail, again, has a hardness of 2.5. So if you scratch that talc with your fingernail and it makes an indentation in it, that means it's softer than your fingernail. So it's very, very soft. There's another mineral in lab, I think, called kaolinite, and it has a hardness of about the same as talc, and it looks like chalk. And this is just a hint for you. Students often confuse talc with kaolinite because kaolinite is just as soft as talc. Specific gravity is simply the relative weight. So if you put two minerals of the same size in both hands and you do this, and one is much heavier than the other one, then it has a high specific gravity. Galena is an example of one that's heavier than it looks. Alright, I'm not going to go through all these because the last three aren't really that important, but the first three are reaction with hydrochloric acid. I'm not sure that hydrochloric acid has been replenished in the lab yet, but if it is, you have these little droppers of hydrochloric acid. And if you drop it on calcite, it will cause a chemical reaction and it will fizz. And that's a really easy one to identify because of this chemical reaction. Magnetism. If it's magnetite, it's a magnet. So you can put a magnet to it and it will stick to it. Taste. If you're brave enough and you make sure the mineral's clean, I don't necessarily advise doing this, but if you get in a pinch and you really need to know, you can find out. So halite tastes like salt because it is salt.
I hope that helps. See you next time.